Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. Why gas giants spin at different speeds? The giant planets of our solar system rotate at speeds that seem almost impossible when you first encounter the numbers. Jupiter, the largest planet, completes a full rotation in just under 10 hours. Imagine standing on a world where a single day passes more than twice as fast as the time it takes to watch a long movie. Saturn spins even faster in some ways, though its rotation is more complex. Uranus and Neptune, the ice giants farther out, rotate at their own distinct rates, each with rotational periods that tell a story about how they formed and what has happened to them over billions of years. Picture Jupiter in your mind, a massive sphere of swirling clouds in shades of cream, brown, orange, and red. This giant world contains more mass than all the other planets combined. Yet it spins so rapidly that it bulges noticeably at its equator. If you could somehow stand at Jupiter's equator, you would be moving at over 28,000 miles per hour, far faster than anything on Earth except spacecraft. The planet's day, the time it takes to complete one rotation, is only about 9 hours and 55 minutes. This incredible speed creates winds that race around the planet in alternating bands, some flowing eastward, others westward, creating the distinctive striped appearance we see in telescopes. But here's where it becomes fascinating. Not all of Jupiter spins at the same rate. The planet is made primarily of hydrogen and helium in gaseous and liquid forms, with no solid surface to anchor to. The equatorial regions spin slightly faster than the polar regions, completing a rotation in about 5 minutes less time. This differential rotation is possible because Jupiter isn't a rigid body like Earth. Different latitudes can rotate at different speeds, sliding past each other in the fluid interior. The deep interior, where hydrogen is compressed into a metallic liquid state, may rotate at yet another rate, one that scientists are still working to measure precisely. Saturn presents an even more puzzling picture. This ringed giant is less dense than water. If you could find an ocean large enough, Saturn would float. Its rapid rotation, with a day lasting only about 10 hours and 33 minutes, causes an even more pronounced equatorial bulge than Jupiter's. The planet's diameter at the equator is nearly 10% larger than its diameter from pole to pole. Picture a sphere that's been squeezed from the top and bottom while being stretched around its middle, all due to the centrifugal force of its rapid spin. What makes Saturn particularly mysterious is that determining its exact rotation rate has proven remarkably difficult. Unlike rocky planets, which have surface features that can be tracked, or planets with strong magnetic fields that rotate with the deep interior, Saturn presents challenges. Its magnetic field is almost perfectly aligned with its rotation axis, which makes it hard to use as a reference. Different methods of measuring Saturn's rotation have given different results, sometimes varying by as much as several minutes. The planet's atmosphere rotates at different speeds, at different latitudes, just like Jupiter's. But figuring out the rotation rate of Saturn's deep interior, the true rotation rate of the planet, remains one of the ongoing puzzles in planetary science. The rings of Saturn add another layer to this story. These rings are made of countless particles of ice and rock, each one orbiting Saturn independently, according to the laws of orbital mechanics. The inner parts of the rings orbit faster than the outer parts, completely independent of how fast the planet itself spins. If you could watch from above Saturn's North Pole, you would see the rings spinning like a vast flat disk, while beneath them the planet rotates at its own separate rate. And within the planet, different layers rotate at their own speeds as well. Now travel farther out to Uranus, the tilted giant. This planet rolls through space like a ball rolling along the ground, with its axis of rotation tilted 98 degrees from the perpendicular to its orbit. Something in Uranus's past, likely a massive collision with another planet-sized object, knocked it onto its side. Despite this dramatic tilt, Uranus rotates relatively quickly, completing one rotation in about 17 hours and 14 minutes. This is slower than Jupiter and Saturn, but still far faster than Earth's 24-hour day. The interior structure of Uranus affects its rotation in ways different from the gas giants. Uranus is classified as an ice giant rather than a gas giant because, beneath its hydrogen and helium atmosphere, it contains a much larger proportion of water, methane, and ammonia ices. These materials, compressed under tremendous pressure, create a layered interior that may not mix as freely as the interiors of Jupiter and Saturn. This layering could mean that different depths within Uranus rotate at substantially different rates, though our knowledge of the planet's interior remains limited from Earth. Neptune, the farthest giant planet, spins with a period of about 16 hours and 6 minutes, slightly faster than Uranus, despite being similar in size and composition. Neptune's deep blue colour comes from methane in its atmosphere, which absorbs red light and reflects blue. Like the other giant planets, Neptune shows differential rotation, with its equatorial atmosphere moving at a different speed than the atmosphere at higher latitudes. The planet has the strongest winds in the solar system, with some storms showing wind speeds exceeding 1,200 miles per hour. These winds don't simply follow the rotation of the planet. They race around at speeds that are faster than the underlying rotation rate, driven by heat flowing from Neptune's interior. The question of why these giants spin at such different speeds takes us back to the formation of the solar system. Imagine the early solar system as a vast rotating disk of gas and dust surrounding the young sun. Within this disk, material began to clump together, forming the seeds of planets. As these clumps grew larger through gravity, pulling in more material, they began to spin faster due to the conservation of angular momentum, the same principle that causes a figure skater to spin faster when pulling their arms in. Each growing planet accumulated material that was already moving in orbit around the Sun. This material had angular momentum, and as it fell onto the growing planet, it transferred that momentum to the planet itself. The amount of spin the planet ended up with depended on exactly how this accretion process occurred, the trajectories of the infalling material, the timing of impacts, and whether the material came in symmetrically or from preferred directions. Jupiter and Saturn, being closer to the Sun and in regions with more available material, grew faster and larger than Uranus and Neptune. Their rapid growth meant they could capture enormous amounts of gas from the protoplanetary disk before it dissipated. This gas fell onto the planets from all directions, and the net effect was to spin the planets up to high rotation rates. The exact speed depended on the complex details of how the gas flowed onto the growing planet and how the planet's gravity interacted with the surrounding disk. The spin rates were also affected by large impacts during the final stages of planet formation. When planet-sized objects collided, they didn't just add their masses together, they also exchanged angular momentum. The angle and speed of impact determined whether the collision would speed up the planet's rotation, slow it down, or even change its axis of rotation. Uranus's extreme tilt almost certainly resulted from one or more giant impacts that occurred late in its formation. Inside these spinning giants, the story continues. The rapid rotation creates strong Coriolis effects that organize the atmospheric flows into bands and zones. Rising warm gas gets deflected by the planet's rotation, creating the jet streams that race around the planets at different latitudes. In Jupiter's case, these jets are remarkably stable, maintaining the same patterns for centuries or longer. The rotation also affects the planet's magnetic fields, which are generated by the movement of electrically conducting fluids in their interiors, liquid metallic hydrogen in Jupiter and Saturn, and perhaps ionic water solutions in Uranus and Neptune. The differential rotation, the fact that different parts of these planets spin at different rates, creates zones of shearing where adjacent layers of fluid slide past each other. These shear zones can become unstable, spawning turbulence and storms. The Great Red Spot on Jupiter, a storm larger than Earth that has persisted for centuries, exists in a region where different wind speeds interact. The storm itself rotates, but at a rate different from the planet's overall rotation, caught in a complex interaction between different atmospheric layers. As these planets continue their journeys around the Sun, their rotation rates change, though extremely slowly. Gravitational interactions with their moons cause tidal effects that gradually transfer angular momentum between the planet and its satellites. This process is the same one that has locked our moon so that it always shows the same face to Earth, though it operates much more slowly on the giant planets due to their enormous masses. Jupiter's large moons are very gradually moving away from the planet, carrying angular momentum with them, which means Jupiter's rotation is slowing down. But this process operates over timescales of billions of years. The interiors of these planets remain largely mysterious, hidden beneath thousands of miles of atmosphere and fluid layers. Scientists use the planet's rotation rates, combined with precise measurements of their gravitational and magnetic fields, to deduce what must be happening in the unseen depths. The exact rotation rate of the deep interior tells us about the distribution of mass within the planet and how rigidly different layers are coupled together. Variations in the gravity field, measured by spacecraft flying past, reveal how mass is distributed between the equator and the poles, which in turn reveals how the rotation has shaped the planet's interior structure. Each of these giant worlds continues to spin through the darkness of space, their days flashing by in fractions of an Earth day, their atmospheres swirling in patterns that have persisted for eons. The differences in their spin rates encode the history of the solar system's formation, the random chance of ancient collisions, and the ongoing physical processes that govern how fluids behave under extreme conditions of pressure, temperature, and rotation. Understanding why gas giants spin at different speeds means understanding not just these four worlds, but the principles that govern planetary formation and evolution throughout the universe, wherever giant planets circle other stars. Why one side of the moon always faces Earth. If you look at the moon on any clear night, you'll see the same familiar pattern of light and dark regions, the features we call the man in the moon or the rabbit, depending on cultural interpretation. This pattern never changes. The same side of the moon perpetually faces Earth. There is no natural rotation of the moon that would show us different faces throughout the month. Ancient astronomers noticed this peculiarity thousands of years ago, and for centuries it seemed like a remarkable coincidence. Why would the moon's rotation period exactly match its orbital period around Earth, both taking about 27 days? The answer involves no coincidence at all, but rather a physical process called tidal locking that inevitably synchronizes the rotation and orbit of any moon close enough to its planet. Tidal locking occurs because of tidal forces, the same forces that create ocean tides on Earth. Tidal forces arise because gravity weakens with distance. The side of Earth facing the moon experiences slightly stronger gravitational pull from the moon than Earth's center does, and Earth's center experiences slightly stronger pull than the side facing away from the moon. This difference in gravitational strength across Earth's diameter creates the tidal force that stretches Earth slightly, raising bulges on both the near and far sides. The same process works in reverse. Earth's gravity creates tidal bulges on the moon, though without oceans these bulges are in the solid rock itself. The moon is slightly elongated, stretched along the Earth-Moon line, with the long axis about 20 meters longer than the short axis. If the moon rotates relative to Earth, These bulges try to rotate with the moon, but Earth's gravity pulls on the bulges, trying to keep them aligned with Earth. Imagine the moon rotating slightly faster than once per orbit. As it rotates, the tidal bulge tries to rotate ahead of the Earth-Moon line. But Earth's gravity pulls more strongly on the closer bulge, creating a torque that opposes the rotation, slowing the moon down. This gravitational torque acts like friction, steadily dissipating the moon's rotational energy. The energy doesn't disappear. It converts into heat through internal friction as the moon flexes slightly, warming the lunar interior by tiny amounts. Over millions of years, this process slows the moon's rotation until it matches the orbital period. Once synchronized, the same side always faces Earth. The tidal bulges align perfectly with the Earth-Moon line, and there's no more torque trying to change the rotation. This is the state the moon reached long ago. The moon is tidally locked to Earth, rotating once on its axis in exactly the same time it takes to orbit Earth once, both periods equal to about 27.3 days. From the moon's perspective, Earth hangs nearly motionless in the lunar sky, drifting slightly back and forth due to libration, small oscillations caused by the moon's slightly elliptical orbit and tilted axis, but never rising or setting. If you stood on the near side of the moon, Earth would always be visible. If you stood on the far side, Earth would never be visible, hence why that hemisphere is sometimes mistakenly called the dark side, though it receives just as much sunlight as the near side. The timescale for tidal locking depends on several factors. Larger tidal forces lock a moon more quickly, closer moons experience stronger tidal forces and lock faster than distant moons. Moons with more internal friction, perhaps from molten interiors, dissipate energy more efficiently and lock faster. For the moon, calculations suggest that tidal locking occurred relatively early in the moon's history, within the first 100 million years or less after its formation. By the time complex life evolved on Earth, the moon had already been showing the same face toward our planet for billions of years. Tidal locking doesn't just affect the moon, it's common throughout the solar system. Most major moons are tidally locked to their planets. Jupiter's 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, all show the same faces to Jupiter. Saturn's large moon Titan is locked. Neptune's moon Triton is locked. In fact, of all the major moons in the solar system, almost everyone is tidally locked to its planet, because they've had billions of years for tidal forces to synchronize their rotations. Some moons have been locked into more complex rotations through resonances with other moons. Mercury, though not a moon, is locked in a 3-to-2 resonance with the Sun. It rotates 3 times for every 2 orbits, a more complex tidal lock. Pluto and its large moon Charon are mutually tidally locked. Each shows the same face to the other always. Pluto rotates once per orbit, and Charon orbits once per Pluto's rotation, so they're perpetually facing each other across their orbit. The tidal locking process also affects Earth, though much more slowly because Earth is more massive than the Moon. The Moon raises tidal bulges on Earth, primarily in Earth's oceans, creating the familiar ocean tides. Earth rotates faster than the Moon orbits. A day is 24 hours, while the Moon's orbital period is about 27 days. This means Earth's rotation carries the tidal bulges ahead of the Moon's position. The bulge closer to the Moon is slightly ahead of the direct Earth-Moon line, and the Moon's gravity pulls backward on this bulge, creating a torque that slows Earth's rotation. This effect is measurable. Earth's rotation is slowing by about 2 milliseconds per century. Days are getting gradually longer as Earth loses rotational angular momentum. The angular momentum doesn't vanish, it's transferred to the Moon's orbit. As Earth slows down, the Moon speeds up slightly in its orbit, and a faster orbital speed means the Moon moves to a higher orbit. The Moon is currently receding from Earth at about 3.8 centimeters per year, precisely measured by bouncing laser beams off retroreflectors left on the lunar surface by Apollo astronauts. This process has been operating throughout Earth's history. Early in Earth's history, when the moon was much closer, days were much shorter, perhaps only 5 or 6 hours long, and the month was shorter too. Ancient corals and other organisms that leave daily growth rings provide evidence for shorter days in the distant past. Going forward, the process will continue. In the far future, if given enough time, tens of billions of years, Earth's rotation would eventually slow to match the moon's orbital period. At that point, Earth would be tidally locked to the moon, just as the moon is now locked to Earth, with the same face of Earth always facing the moon. However, this will never happen because the sun will evolve into a red giant in about 5 billion years, long before Earth could become tidally locked to the moon. The expanding sun will engulf the inner solar system, making the question of Earth's rotation academic at best. The tidal locking of the moon has significant consequences for lunar exploration and observation. The far side of the moon remained completely unknown until spacecraft flew around it. The Soviet Luna 3 probe in 1959 captured the first images of the far side, revealing a surface surprisingly different from the near side. The far side has many more craters and far fewer of the dark volcanic plains called Maria that dominate the near side's appearance. This asymmetry likely relates to the moon's tidal locking. The near side experienced more volcanic activity, possibly because Earth's gravity affected the moon's internal structure and thermal evolution. Communication with spacecraft on the lunar far side requires relay satellites because direct signals cannot reach Earth from there. China's Chang'e 4 mission, which landed on the far side in 2019, used a relay satellite positioned beyond the moon to maintain communication. Future lunar bases on the far side would face this same communication challenge, requiring either relay satellites or cables running over the lunar surface to the near side. Tidal locking affects more than just moons. Many exoplanets discovered orbiting close to their stars are likely tidally locked, with one hemisphere permanently facing the star in daylight, while the other remains in eternal darkness. These planets, particularly those orbiting red dwarf stars, where the habitable zone is very close to the star, would have extreme temperature contrasts between their day and night sides. Understanding how atmospheres redistribute heat on tidally locked planets is crucial for assessing their potential habitability. The fact that one side of the moon always faces Earth is not a lucky accident, but the inevitable result of physical forces operating over immense timescales. Every moon close enough to its planet will eventually lock, synchronizing its rotation to its orbit. The moon reached this state billions of years ago, and it will remain locked for the remaining lifetime of the Earth-Moon system. The same face that witnessed Earth's formation, the rise of life, the age of dinosaurs, and the emergence of humanity will continue watching Earth for billions of years to come, held in place not by chance but by the patient, inexorable work of tidal forces that have shaped orbital dynamics since the solar system formed, creating the familiar face we see in the night sky every month, unchanging and eternal from our human perspective, yet itself the product of changes stretching across geological deep time. Why space is nearly empty? When you look up at the night sky, space appears crowded with stars, planets, and galaxies. Photographs from telescopes show spectacular images of colourful nebulae, dense star clusters, and brilliant galaxies packed with hundreds of billions of stars. These images create an impression of a cosmos teeming with matter, a universe filled to the brim with celestial objects. But this impression is profoundly misleading. Space is almost unimaginably empty. The distances between objects are so vast and the objects themselves so small relative to those distances that if you could somehow travel to a random location in the universe, the overwhelming likelihood is that you would find yourself surrounded by nothing. No stars, no planets, no gas, no dust, for distances stretching farther than you could travel in a lifetime, even at the speed of light. To understand just how empty space is, consider the space between Earth and the Moon. The Moon orbits at an average distance of about 380,000 kilometers from Earth. That's far enough that you could fit all the other planets in the solar system side by side in the gap between Earth and the Moon, with room to spare. Now imagine taking a sphere with a radius equal to this Earth-Moon distance. Within that enormous volume, there are only two objects of any significant size, Earth and the Moon themselves. Everything else is emptiness, with only occasional atoms of gas or tiny dust particles scattered throughout. The situation becomes even more extreme when you consider the space between planets. Earth orbits about 150 million kilometers from the Sun. Mars orbits about 230 million kilometers from the Sun. The distance between Earth and Mars varies as both planets orbit, but at their closest approach, they're separated by about 55 million kilometers. This vast gulf contains essentially nothing. No planets, no moons, just a scattering of asteroids so small and so far apart that even if you were travelling through this region, you would be extraordinarily unlikely to come anywhere near one. The asteroid belt, often depicted in science fiction as a dense field of tumbling rocks that spaceships must carefully navigate, is in reality astonishingly sparse. The belt contains hundreds of thousands of asteroids larger than 1 kilometer across and millions of smaller ones. This sounds like a lot, and by the standards of everyday experience it is. But these asteroids are spread across an enormous volume of space, a region extending from about 300 million kilometers to 500 million kilometers from the Sun, and spanning the full circumference around the Sun at these distances. The result is that the average distance between asteroids is measured in millions of kilometers. If you were to travel through the asteroid belt, you would see nothing for days or weeks of travel before coming near even a single asteroid. The density of matter in the asteroid belt averages far less than 1 particle per cubic kilometer. Compare this to air at sea level on Earth, which contains about 10 to the 25th particles per cubic kilometer, a 1 followed by 25 zeros. The asteroid belt, despite containing countless asteroids, is millions of billions of times less dense than the air you're breathing right now. Every spacecraft we've sent through the asteroid belt, and many have made the journey, has passed through without incident, without needing to dodge asteroids, simply because the belt is so incredibly empty. Beyond the planets, the emptiness becomes even more profound. The nearest star to our Sun, Proxima Centauri, lies about 40 trillion kilometers away, a distance so vast that light, travelling at 300,000 kilometers per second, takes over 4 years to cross it. If you scaled the Sun down to the size of a basketball, Earth would be a grain of sand orbiting about 25 meters away, and Proxima Centauri would be another basketball more than 6,000 kilometers away. The sphere of space between these two basketballs contains essentially nothing. No planets, no asteroids, no comets that we know of, just occasional atoms of hydrogen, some dust particles so rare you could travel for years without encountering one, and the faint pressure of starlight. This interstellar space contains gas, but calling it gas seems almost misleading given its extreme tenuousness. In the space between stars, the density averages about 1 atom per cubic centimeter. For comparison, air at sea level contains about 10 to the 19th atoms per cubic centimeter. Interstellar space is less dense than air by a factor of 10 million trillion. The best vacuum we can create in laboratories on Earth, in the most sophisticated vacuum chambers, is still millions of times denser than the average density of interstellar space. Even the densest regions of interstellar space, the molecular clouds where stars form, are extraordinarily sparse by terrestrial standards. These clouds, which appear dark and opaque in photographs because they block light from stars behind them, contain perhaps 1 million atoms per cubic centimeter at their densest cores. This is dense for space, but it's still 10 trillion times less dense than air on Earth, You could travel through the densest part of a molecular cloud and not even notice. There would be no resistance to your motion, no sense of passing through anything. The emptiness extends to larger scales as well. Our Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, along with vast quantities of gas, dust, and dark matter. Yet these hundreds of billions of stars occupy a disk about 100,000 light-years across and roughly 1,000 light-years thick at the Sun's location. The stars are so far apart that if you were to travel to a random location within the galaxy, you would find yourself in interstellar space, far from any star. The average distance between stars is about 5 light-years. At the scale where stars are separated by light-years, the stars themselves, objects typically about 1 million kilometers across, are essentially point-like. They occupy a negligible fraction of the galaxy's volume. Between galaxies, the emptiness reaches its most extreme. The space separating galaxies is called intergalactic space, and it's even emptier than interstellar space. The density of matter in intergalactic voids, the enormous empty regions between galaxy clusters, is approximately 1 atom per 10 cubic meters. Think about that. You could take a cube of space 10 meters on each side, large enough to contain a small house, and on average, it would contain just one single atom. This is as close to perfect vacuum as nature achieves anywhere in the universe. The scale of intergalactic distances staggers comprehension. The Andromeda Galaxy, the nearest large galaxy to our Milky Way, lies about 2.5 million light-years away. The space between our galaxy and Andromeda is largely empty, except for a few dozen small dwarf galaxies and some scattered gas clouds. Beyond our local group of galaxies, the distances grow even more immense. The Virgo cluster of galaxies, which contains thousands of galaxies, lies about 50 million light-years away. The space between galaxy clusters is measured in tens of millions to hundreds of millions of light-years, and it contains essentially nothing. So why is space so empty? The answer lies in how the universe evolved after the Big Bang. In the earliest moments, the universe was actually extremely dense. All matter and energy were compressed into a tiny volume. But the universe has been expanding ever since, and as it expands, the matter within it spreads out, becoming less and less dense. The expansion of space itself increases the distances between objects, diluting the average density of matter throughout the cosmos. Gravity works against this dilution by pulling matter together into clumps. Regions that were slightly denser than average in the early universe attracted more matter, becoming denser still, while regions that were slightly less dense lost matter to the denser regions and became emptier. Over billions of years, this process created the structure we see today. Matter concentrated into stars, which are concentrated into galaxies, which are concentrated into galaxy clusters and superclusters with vast voids between them. But even with gravity concentrating matter into structures, the vast majority of space remains empty because the fundamental ratio of matter to space is so low. If you took all the matter in the observable universe, every atom in every star, planet, gas cloud and galaxy, and spread it uniformly throughout all of space, the density would be about 5 atoms per cubic meter. This is the average density of the universe, and it reveals that matter is extremely rare. The universe is about 5 atoms of matter per cubic meter on average, with the rest being empty space and dark energy. The emptiness of space has profound implications. It means that collisions between stars are extraordinarily rare, even in the centers of galaxies, where stars are most densely packed. When two galaxies collide, and galaxy collisions are fairly common on cosmic timescales, the stars themselves almost never hit each other. The galaxies pass through each other, like two clouds of gnats interpenetrating, without individual gnats colliding, because the distances between stars are so large compared to the stars' sizes. The emptiness also means that space travel is, in some ways, easier than it might otherwise be. A spacecraft traveling through space doesn't need to constantly dodge debris or navigate through fields of material. Space is clear. The challenges of space travel come not from crowding but from the vast distances between destinations and the energy required to cross those distances. Light from distant objects travels through this emptiness for billions of years, crossing intergalactic voids, interstellar space, and the relative crowding of planetary systems to eventually reach our telescopes. The fact that we can see distant galaxies at all, objects billions of light years away, testifies to how empty space is. If space were filled with gas or dust at densities even remotely approaching terrestrial conditions, the light would be scattered and absorbed long before travelling such distances. The emptiness of space is not a coincidence or an accident. It's a fundamental consequence of the universe's expansion, the initial density of matter after the Big Bang, and the way gravity organises that matter into structures. The spectacular images of galaxies, nebulae, and star clusters show us the rare locations where matter has concentrated. But these are the exceptions, the islands of matter in an ocean of emptiness. The typical state of the universe is not the crowded star field or the dense nebula. It's the dark, cold, nearly perfect vacuum of intergalactic space, where a single atom might drift alone for years before encountering another, where the nearest star is so distant that its light takes millions of years to arrive, and where the overwhelming reality is not presence but absence, not matter but void, not something but nothing, extending in all directions for distances that dwarf the span of human comprehension. Why some planets have no moons? Of the 8 major planets in our solar system, 2 orbit the Sun without any natural satellites. Mercury and Venus have no moons. This seems puzzling at first. Mars, smaller than either Mercury or Venus, has 2 small moons. Earth has 1 large moon. The giant planets beyond Mars have dozens or even hundreds of moons. Why would some planets capture or retain moons while others remain moonless? The answer involves a complex interplay of gravitational dynamics, orbital mechanics, planetary formation history, and the specific environments in which these planets exist. The first factor to consider is proximity to the Sun. Mercury, the innermost planet, orbits at an average distance of only 58 million kilometers from the Sun. Venus orbits at 108 million kilometers. At these distances, the Sun's gravitational influence is overwhelming. For a moon to remain in a stable orbit around a planet, it must orbit within a region called the Hill sphere, the volume of space where the planet's gravity dominates over the Sun's gravity. The Hill sphere's size depends on the planet's mass and its distance from the Sun. The farther from the Sun, the larger the Hill sphere. The more massive the planet, the larger the Hill sphere. Mercury's Hill sphere extends only about 175,000 kilometers from the planet, less than half the distance from Earth to our Moon. Venus's Hill sphere is larger, extending about 1 million kilometers. But these regions are small compared to the Hill spheres of the outer planets. Earth's Hill sphere extends about 1.5 million kilometers. Jupiter's extends about 50 million kilometers. The small hill spheres around Mercury and Venus mean there's simply less space where a moon could maintain a stable orbit. But having a small hill sphere doesn't automatically prevent moon formation or capture. The real problem comes from tidal forces exerted by the Sun. Tidal forces arise because gravity weakens with distance, creating a differential pull across an extended object. The Sun's tidal forces on a potential moon of Mercury or Venus would be much stronger than the tidal forces experienced by moons of more distant planets, simply because these inner planets are so close to the Sun. These solar tides compete with the planet's own gravity for control of the moon's orbit. Over time, solar tidal perturbations can destabilize a moon's orbit, causing the orbit to become increasingly elliptical or inclined. Eventually, the moon might either crash into the planet, drift away into an independent orbit around the Sun, or get ejected from the system entirely. The closer the planet is to the Sun, the stronger these destabilizing effects become. There's a critical region around each planet, well inside the Hill sphere, where orbits can remain stable over billions of years despite solar perturbations. This region is typically only about 1/3 to 1/2 the radius of the Hill sphere. For Mercury, this stable region extends perhaps only 60,000 to 80,000 kilometers from the planet. For Venus, perhaps 300,000 to 500,000 kilometers. Any moon orbiting farther out would likely be stripped away by solar tides over geological time. But this raises another question. Why didn't small moons form or get captured in these inner stable regions? To understand this, we need to consider how moons form in the first place. There are three primary mechanisms: co-formation, where the moon forms from the same disk of material as the planet; capture, where the planet's gravity snares a passing object; and giant impact, where debris from a massive collision coalesces into a moon. The giant impact hypothesis explains Earth's moon. About 4.5 billion years ago, a Mars-sized object called Theia collided with the young Earth. The impact ejected enormous amounts of material into orbit around Earth, and this debris quickly coalesced into the moon. This mechanism requires specific conditions, a large impactor at the right velocity and angle. Mercury and Venus likely experienced giant impacts during the chaotic early solar system, but any moons formed from such impacts would face additional challenges. Mercury's proximity to the Sun means that debris from an impact would orbit in an environment where solar tides are extremely strong. Material orbiting Mercury would experience differential forces from the Sun that could prevent it from coalescing into a moon, or could destabilize any moon that did form. Additionally, Mercury's slow rotation, it rotates once every 59 Earth days, means it couldn't have transferred much angular momentum to a moon through tidal interactions, which helps stabilize moon orbits over time. Venus presents a different puzzle. It's larger than Mercury, more massive, and farther from the Sun, with a correspondingly larger Hill sphere and stable region. Venus should be able to retain a moon more easily than Mercury, yet Venus is moonless. Several theories attempt to explain this anomaly, and the answer might involve Venus's unique rotation. Venus rotates incredibly slowly. One Venusian day lasts 243 Earth days, and it rotates backward relative to its orbital motion, a condition called retrograde rotation. This retrograde rotation is unusual and likely resulted from one or more giant impacts that altered Venus's spin. If Venus once had a moon formed from such an impact, the combination of Venus's slow retrograde rotation and solar tides could have caused the moon to spiral inward rather than outward. On Earth, tidal interactions with the moon cause the moon to gradually recede. It's moving away from Earth at about 3.8 centimeters per year. This happens because Earth's rotation is faster than the moon's orbital period, so tidal bulges on Earth are carried ahead of the Earth-Moon line, pulling the moon forward in its orbit and transferring angular momentum. For a moon orbiting retrograde Venus, or orbiting a very slowly rotating Venus, the tidal dynamics work differently. The tidal bulges would lag behind rather than lead, causing the moon to lose orbital energy and spiral inward toward the planet. Eventually, the moon would cross the Roche limit, the distance inside which tidal forces overcome the moon's self-gravity, and be torn apart. The fragments would either fall onto Venus or spread into a ring system that gradually decayed, with particles spiraling down to the planet's surface over millions of years. If Venus had a moon in the distant past, this mechanism could have destroyed it billions of years ago. Alex Alemi and David Stevenson proposed this scenario in 2006, suggesting that Venus's slow retrograde rotation would cause any moon to spiral inward and be destroyed within tens of millions of years. Their calculations showed that even a large moon, similar in size to Earth's moon, would meet this fate if Venus rotated slowly enough. The giant impact that created the moon might also have been responsible for slowing or reversing Venus's rotation, setting up the conditions for the moon's eventual destruction. Capture represents another moon formation mechanism, but it faces significant challenges. For a planet to capture a passing asteroid or other object, something must remove energy from the object's orbit during the close encounter. Otherwise, the object simply swings past the planet and continues on its way. Energy can be removed through atmospheric drag if the planet has a thick atmosphere, through gravitational interactions with existing moons in a three-body interaction, or through tidal forces if the encounter is extremely close. Mercury has essentially no atmosphere, so atmospheric capture is impossible. Venus has a thick atmosphere, but capturing an object large enough to be considered a moon rather than just a small asteroid would require the object to pass through the upper atmosphere at just the right velocity and angle, an unlikely scenario. Mars's two small moons, Phobos and Deimos, might be captured asteroids, but they're tiny. Phobos is only about 22 kilometers across and Deimos about 12 kilometers. Mars likely captured them during the early solar system when more debris was available and orbital dynamics were more chaotic. For Mercury and Venus, the combination of their locations in the inner solar system, where fewer large objects were available for capture, and the difficulty of the capture process itself, meant that gravitational capture of moons was unlikely. The inner solar system was largely cleared of debris early in solar system history, as objects either accreted into planets, fell into the sun, or were ejected to the outer system through gravitational interactions with the growing planets. The composition and formation history of the inner planets also matters. Mercury, Venus, Earth, and Mars formed from the inner portion of the protoplanetary disk, where temperatures were too high for ice to condense. These planets formed primarily from rocky and metallic materials. The giant planets formed farther out, where ices could exist, providing more material for planet and moon formation. The abundance of material in the outer solar system, both for forming the planets themselves and for forming moons, was simply greater than in the inner solar system. The giant planets likely formed their large regular moons, the major satellites that orbit in the planet's equatorial plane, from circumplanetary disks, miniature versions of the protoplanetary disk that surrounded the young sun. These disks contained enough material to form multiple large moons. Jupiter's four Galilean moons, Io, Europa, Ganymede, and Callisto, discovered by Galileo Galilei in 1610, formed this way. Saturn's major moons, including Titan, formed similarly. The inner planets, with less mass and forming in a region with less available material, likely didn't have substantial circumplanetary disks, making it difficult to form moons through this mechanism. Exoplanet studies have revealed that moonless planets might be quite common. Many exoplanets discovered so far are hot Jupiters, gas giants orbiting extremely close to their host stars, often closer than Mercury orbits the Sun. These planets, despite being massive, likely have no moons because the extreme proximity to their stars creates even more severe tidal effects than Mercury experiences. Any moons would be quickly stripped away by stellar tides. Some hot Jupiters may have had moons when they formed farther from their stars, but lost them as the planets migrated inward to their current close-in orbits. Other exoplanets orbit in the habitable zones of their stars at distances where moons could potentially remain stable. Whether these planets have moons depends on their formation history, the availability of material for moon formation, and the dynamical environment in which they formed. Detecting exomoons, moons orbiting exoplanets, remains at the edge of current observational capabilities, though several candidates have been proposed. As detection techniques improve, we'll learn whether most planets have moons or whether moonless planets are actually the norm. The absence of moons around Mercury and Venus is not a deficiency, but rather a natural consequence of where these planets are located and how they formed. Their proximity to the Sun creates an environment where moons cannot easily form or survive over billions of years. Any moons that might have existed in the early solar system were likely destroyed by solar tides, spiraled into the planets due to tidal interactions with slowly rotating worlds, or were ejected from unstable orbits. The planets that do have moons, Earth, Mars, and especially the giant planets, possess them because they orbit farther from the Sun, where Hill spheres are larger, solar tides are weaker, and the environment is more conducive to moon formation and retention, showing that the presence or absence of moons depends not on the planet's inherent qualities, but on the orbital and environmental context in which the planet exists, making our own moon's existence not a given, but rather the result of a fortunate combination of location, timing, and the specific collision that created it billions of years ago. Why silicon-based life forms might be possible. For as long as scientists have contemplated life beyond Earth, one element has persistently captured imaginations as a possible alternative to carbon, silicon. Science fiction has explored silicon-based aliens in countless stories, from rock-like creatures that metabolize minerals to crystalline beings that think at geological timescales. But these fictions rest on a foundation of genuine chemistry. Silicon sits directly below carbon in the periodic table, shares many of carbon's most important properties, and is far more abundant in Earth's crust than carbon. Yet despite this abundance and chemical similarity, silicon never became the basis for life on Earth. Understanding why silicon-based life might still be possible elsewhere requires examining both the remarkable parallels between silicon and carbon chemistry and the significant obstacles that would need to be overcome. Carbon's dominance in biochemistry stems from several key properties. Carbon atoms can form 4 strong covalent bonds with other atoms, allowing them to link together into chains, branches, and rings of almost unlimited complexity. A single carbon atom might bond to 4 other carbon atoms, creating a 3-dimensional network. Or carbon atoms might link into chains hundreds or thousands of atoms long, with various other elements, hydrogen, oxygen, nitrogen, phosphorus, sulfur, attached at different positions. This versatility allows carbon to form millions of different molecules, from simple methane with 1 carbon atom to DNA molecules containing billions of carbon atoms arranged in precise sequences that store genetic information. Silicon shares carbon's ability to form 4 covalent bonds. The electron configuration that gives carbon its bonding properties is mirrored in silicon, making silicon capable of forming similar structures, silicon chains, silicon rings, silicon networks. In fact, silicon chemistry forms the basis of an entire class of synthetic materials called silicones, which consist of chains of alternating silicon and oxygen atoms with organic groups attached. These materials, familiar as sealants, lubricants, and medical implants, demonstrate that silicon can indeed form large complex molecules. But silicones are human inventions, created in laboratories and factories. Nature has not produced silicon-based organisms, at least not on Earth, despite silicon being about 900 times more abundant in Earth's crust than carbon. The primary obstacle to silicon-based life under Earth-like conditions is silicon's relationship with oxygen. When carbon reacts with oxygen, when it burns, it forms carbon dioxide, a gas at normal Earth temperatures. This gas can be easily expelled from an organism and recycled back into the environment. Plants take in carbon dioxide and use it to build sugars through photosynthesis. Animals exhale carbon dioxide as a waste product of metabolism. Carbon dioxide dissolves readily in water, allowing it to be transported in blood and participate in various chemical reactions. The carbon cycle that sustains Earth's biosphere depends on carbon dioxide being gaseous, mobile, and chemically accessible. Silicon's equivalent compound is silicon dioxide, silica, quartz, sand, rock. When silicon burns with oxygen, it forms a solid. This solid is extremely stable, nearly insoluble in water, and chemically unreactive under normal conditions. An organism that metabolizes silicon and oxygen the way Earth organisms metabolize carbon and oxygen would accumulate solid mineral waste inside its body or would need to excrete sand. The waste products of silicon metabolism cannot easily be transported in fluids, cannot be exhaled as gas, and cannot be recycled through environmental cycles the way carbon dioxide can. This fundamental difference makes silicon-oxygen chemistry poorly suited for biochemistry on worlds with oxygen-rich atmospheres and liquid water. However, removing oxygen from the equation changes the possibilities dramatically. In environments where oxygen is absent or rare, silicon chemistry behaves very differently. Silicon forms stable bonds with hydrogen, creating silanes, molecules analogous to hydrocarbons, but with silicon replacing carbon. The simplest silane is silane itself, with one silicon atom bonded to 4 hydrogen atoms, analogous to methane. Longer chains are possible: disilane with 2 silicon atoms, trisilane with 3, and so on. These silicon-hydrogen chains are reactive and unstable compared to carbon-hydrogen chains, but in the absence of oxygen, they might persist long enough to serve biological functions. Temperature plays a crucial role in silicon chemistry. At Earth's surface temperatures, silicon-silicon bonds are relatively weak compared to carbon-carbon bonds. Silicon compounds tend to break apart more easily, making long, stable silicon chains difficult to maintain. But at much colder temperatures, the kinds found in the outer solar system, silicon chemistry becomes more favorable. Chemical reaction rates slow down dramatically at low temperatures, which could actually help stabilize silicon compounds that would rapidly decompose at room temperature. Meanwhile, some of the alternative solvents that might replace water at these temperatures could interact with silicon compounds in ways that favor complex chemistry. Liquid methane and ethane, which exist naturally on Saturn's moon Titan at temperatures around -180 degrees Celsius, represent one possibility. In these hydrocarbon seas, water is as hard as rock and oxygen is locked away in ice and minerals. Silicon compounds might dissolve in liquid hydrocarbons more readily than in water, and without oxygen to react with, silicon could potentially form the complex, diverse molecules that life requires. The chemistry would be radically different from Earth's biochemistry. Reaction rates would be thousands of times slower, molecules would have different shapes and properties, and the fundamental mechanisms of energy storage and information transfer would need to be reimagined. But the basic requirements for life, complex molecules that can store information, catalyze reactions, and self-replicate, might still be achievable with silicon as the central element. Liquid nitrogen, which exists at even colder temperatures, offers another potential solvent. Nitrogen becomes liquid at -196 degrees Celsius at Earth atmospheric pressure. A world with lakes or oceans of liquid nitrogen would be incomprehensibly cold by Earth standards, but chemical reactions would still occur, just very slowly. Silicon compounds might be more stable and diverse at these extreme temperatures, allowing them to form the kinds of complex structures that life needs. Another approach to silicon-based life involves thinking beyond complete replacement of carbon. Instead of imagining organisms built entirely from silicon, consider hybrid biochemistries that use both elements. Silicon might form structural components, while carbon handles information storage and catalysis. Silicon-oxygen minerals could serve as skeletal elements, providing rigid support structures that carbon-based soft tissues attach to. This is essentially what Earth organisms do. Bones, shells, and the glass-like structures of diatoms all incorporate silicon compounds, though the fundamental biochemistry remains carbon-based. A true silicon-based organism would integrate silicon more deeply into its biochemistry, perhaps using silicon-containing molecules for energy storage, membrane structure, or even genetic material. The information storage challenge represents one of the most significant hurdles for silicon-based life. DNA and RNA work remarkably well as information storage molecules because they're stable enough to preserve information over time, but flexible enough to be copied and modified. The sugar phosphate backbone provides structural support, while the nitrogen bases store actual information through their sequence. Could silicon replace the carbon in the sugar molecules? Silicon-containing analogues of sugars and nucleotides have been synthesized in laboratories, demonstrating that such molecules can exist. Whether they could reliably store and transmit information across generations in a living organism remains unknown, but the chemistry doesn't appear to forbid it outright. Energy metabolism in silicon-based organisms presents another puzzle. Earth organisms primarily extract energy by rearranging chemical bonds, breaking bonds in food molecules, and forming new bonds in waste products, capturing the released energy in the chemical bonds of ATP. Silicon-based organisms would need analogous processes. Perhaps they could oxidize silanese to release energy, though the solid silicon dioxide waste product would be problematic. Or they might use entirely different metabolic pathways based on silicon's interaction with halogens like fluorine or chlorine, creating different waste products that could be more easily managed. In extremely cold environments, metabolic rates could be extraordinarily slow. A silicon-based organism might take years to grow or reproduce, operating on timescales that would make watching grass grow seem rapid by comparison. The evolution of silicon-based life would require a planet with very specific conditions. Silicon would need to be available in reactive forms rather than locked into stable minerals. The temperature would probably need to be very cold to favor silicon chemistry over its tendency to decompose. Oxygen would need to be absent or rare to prevent silicon from forming insoluble silicon dioxide. A suitable solvent other than water would need to exist: liquid hydrocarbons, liquid ammonia, or something even more exotic. These conditions might exist on certain moons in the outer solar system, on rogue planets drifting through interstellar space, or on exoplanets orbiting dim red dwarf stars, where temperatures never rise above the freezing point of water. Titan, with its lakes of liquid methane and ethane, its thick nitrogen atmosphere, and its extremely cold temperatures, represents perhaps the best candidate in our solar system for silicon-based life. NASA's Dragonfly mission, scheduled to launch in the late 2020s, will explore Titan's surface and could potentially detect signs of exotic biochemistry if it exists. The mission won't specifically look for silicon-based life. Nobody knows exactly what signatures such life would produce, but it will analyze organic chemistry in Titan's lakes and atmosphere, searching for patterns that might indicate biological processes. Even if silicon-based life exists nowhere in the universe, studying the possibility expands our understanding of chemistry's relationship to biology. It forces us to question our assumptions about what life requires and what forms it might take. Every element brings different properties, different strengths and weaknesses, different possibilities and constraints. Carbon happened to be the element that worked on Earth under Earth's conditions, but Earth represents just one set of conditions among countless possibilities across the universe. The theoretical possibility of silicon-based life also highlights a challenge in searching for extraterrestrial life. Most of our detection methods assume life will be similar to Earth's, producing oxygen, methane, or other gases we associate with biological activity, building structures we would recognize using chemistry we understand. But silicon-based life operating in liquid methane seas at minus 180 degrees Celsius would produce completely different signatures. It might metabolize compounds we consider inert waste products, and excrete substances we consider essential for life. Its waste products might be our nutrients, and vice versa. We might look directly at a world covered in silicon-based organisms and not recognize it as inhabited because we're searching for carbon signatures. Silicon-based life might be possible in environments so different from Earth that the very definition of life becomes strained. Perhaps silicon-based entities would be better described as self-organizing chemical systems rather than organisms in any sense we would recognize. They might grow and reproduce on timescales of centuries. Their metabolism so slow that a single thought, if they think at all, might take years to form. They might not have discrete bodies with clear boundaries between self and environment, but instead exist as diffuse networks of silicon-based chemistry spread across vast areas. They might not die in any meaningful sense, but simply cease maintaining organization and gradually disperse back into their environment. Why silicon-based life forms might be possible comes down to chemistry being flexible, creative, and opportunistic. The laws of chemistry operate everywhere in the universe, but they produce different outcomes under different conditions. Silicon's chemical properties give it potential as a basis for complex, self-organizing systems under the right circumstances. Circumstances that apparently don't exist on Earth, but might exist elsewhere. From the hydrocarbon lakes of Titan to hypothetical ice worlds, orbiting dim stars to environments we haven't yet imagined, silicon might be constructing molecules, storing information, and powering metabolisms in ways that parallel carbon-based life, just enough to recognize as living while remaining alien enough to challenge everything we thought we knew about biology, proving that life's possibilities extend beyond the single example we know to encompass chemistries as diverse as the cosmos itself. How asteroids can have their own moons. The first asteroid moon was discovered in 1993, when the Galileo spacecraft, on its way to Jupiter, flew past an asteroid named Ida and transmitted images showing a small companion orbiting it. The discovery surprised many scientists. Ida itself is only about 56 kilometers long, an irregular, potato-shaped chunk of rock tumbling through space. Its tiny moon, later named Dactyl, measures merely 1.4 kilometers across. How could such a small object, with such weak gravity, possibly hold onto a moon? This discovery opened an entirely new chapter in our understanding of asteroids, revealing that these ancient fragments of the early solar system are far more complex and dynamic than anyone had imagined. The key to understanding asteroid moons lies in recognizing that gravity, no matter how weak, still operates according to the same laws, whether you're considering a massive planet or a tiny asteroid. Every object with mass generates a gravitational field, and that field extends infinitely into space, weakening with distance, but never disappearing entirely. An asteroid's gravity is incredibly feeble compared to a planet's. Ida's surface gravity is only about 0.3 to 1% of Earth's, depending on where you measure it, on the irregular surface. But this tiny gravitational pull is sufficient to influence nearby objects, and under the right circumstances, it can capture and hold a moon in orbit. The mechanics of orbital motion around an asteroid differ significantly from orbits around planets. Planets are generally spherical, or nearly so, which means their gravitational fields are relatively simple. They approximate the field of a point mass located at the planet's center. Asteroids, however, are often highly irregular, shaped like elongated potatoes, peanuts, or even contact binaries where two lobes are stuck together. This irregular shape creates a complex gravitational field with multiple peaks and valleys, regions where the gravitational pull is stronger or weaker than average. An object orbiting an irregular asteroid doesn't follow a simple ellipse the way a planet orbits the Sun. The orbit wobbles and shifts due to the uneven gravity field. Additionally, Most asteroids rotate, and this rotation causes the gravitational field to change over time from the perspective of an orbiting object. The combination of irregular shape and rotation creates a challenging environment for stable orbits. Yet despite these complications, asteroid moons not only exist but are surprisingly common. Current estimates suggest that about 15% of near-Earth asteroids have companions, and the fraction is even higher among certain populations. Asteroid moons form through several mechanisms, each revealing something about the dynamic processes that shape these small bodies. The first mechanism is capture. Similar to how planets can capture moons, though the process works differently at asteroid scales. When two asteroids pass close to each other, they normally just fly past, perhaps exchanging some momentum through gravitational interaction, but remaining on separate trajectories. However, if a third body is nearby during the encounter, it can absorb some of the kinetic energy through a three-body gravitational interaction, allowing one asteroid to be captured into orbit around the other. This three-body capture was more common in the early solar system, when asteroids were more numerous and encounters more frequent. The asteroid belt, located between Mars and Jupiter, contains hundreds of thousands of asteroids larger than 1 kilometer and millions of smaller ones. In the denser environment of the early solar system, close encounters between 3 or more asteroids occurred regularly, providing opportunities for capture. Once captured, the orbit would gradually stabilize through tidal interactions and additional gravitational perturbations. Collisions represent another pathway to moon formation. The asteroid belt is a violent place where collisions occur regularly on geological timescales. When two asteroids collide, the impact doesn't necessarily destroy both objects. Depending on the impact velocity and angle, a collision might excavate a crater and eject material into space. Some of this ejected material falls back onto the asteroid, but some of it enters orbit around the shattered parent body. Over time, these orbiting fragments can collide with each other and coalesce into a moon. The collision scenario explains why many asteroid moons orbit very close to their parents and have compositions similar to the parent asteroid. If a moon formed from impact debris, it would naturally be made of the same material as the parent. Studies of asteroid pairs, asteroids with very similar orbits and compositions, suggest that many originated as fragments from catastrophic collisions that split a parent asteroid into 2 or more large pieces. In some cases, these pieces remain gravitationally bound, creating a binary asteroid system. The YORP effect provides a third mechanism for creating asteroid moons, and it's one of the most fascinating processes in asteroid dynamics. YORP stands for Yarkovsky-O'Keefe-Radzievsky-Paddock, named after the scientists who contributed to understanding this phenomenon. The YORP effect occurs when sunlight reflecting off an asteroid's irregular surface creates tiny torques that gradually change the asteroid's rotation rate. The effect is incredibly small. It might change an asteroid's rotation period by only milliseconds per year, but over millions of years, these tiny changes accumulate. As the YORP effect spins an asteroid faster and faster, centrifugal forces at the equator increase. Eventually, the asteroid might be rotating so fast that material at the equator experiences outward centrifugal forces that exceed the inward gravitational forces. At this point, material begins to lift off the surface and enter orbit, forming a ring or disk around the asteroid. This orbiting material can then aggregate into one or more moonlets. Computer simulations and observations of very rapidly rotating asteroids support this mechanism. Asteroid 1999 KW4 provides a clear example of the YORP effect in action. This binary asteroid system consists of a larger primary asteroid, about 1.3 kilometers in diameter, rotating once every 2.8 hours, extremely fast for an object this size. A smaller satellite, about 360 meters across, orbits the primary at a distance of about 2.6 kilometers. the primary asteroid has a distinct equatorial ridge, exactly what would be expected if centrifugal forces had been pushing material toward the equator. The satellite likely formed from material that was flung off this equatorial region when the primary was spinning even faster in the past. The rotation rates of asteroids play a crucial role in their ability to hold moons. There's a limiting rotation rate, typically around one rotation every 2 to 3 hours for a solid asteroid, beyond which centrifugal forces would tear the asteroid apart. This limit, called the critical spin limit, depends on the asteroid's size, shape, and material strength. Asteroids can spin faster than this limit only if they're held together by internal strength, essentially solid rocks, rather than just gravity. Many asteroids appear to be rubble piles, loose aggregations of boulders and gravel, held together primarily by their own weak gravity, with little internal strength. These rubble pile asteroids cannot spin faster than the critical limit without shedding material or breaking apart. The Roche limit becomes relevant for asteroid moons, just as it does for planetary moons. The Roche limit is the distance inside which tidal forces would tear apart a satellite that's held together only by its own gravity. For solid objects held together by material strength, they can orbit inside the Roche limit without being destroyed, though they experience severe tidal stresses. Many asteroid moons orbit near or even slightly inside the classical Roche limit for a fluid body, suggesting that they're solid objects with sufficient strength to resist tidal disruption. Binary asteroids, where two similarly sized objects orbit their common center of mass, represent a special category. In these systems, neither object is clearly the moon of the other. They're more like double asteroids, co-orbiting companions. The Pluto-Charon system is arguably a binary system, though Pluto is now classified as a dwarf planet rather than an asteroid. Among smaller asteroids, binary systems are not uncommon. The asteroid Antiope consists of two objects, each about 88 kilometers in diameter, orbiting their common center of mass at a separation of about 170 kilometers. These binary systems likely form from gentle collisions or from the splitting of a rapidly rotating parent body. When an asteroid spins fast enough, it can develop a dumbbell or peanut shape, elongated along its equatorial plane. If the spin increases further, the dumbbell can split at its narrow center, creating two separate bodies. Because they formed from the same parent, they initially have very similar velocities and remain gravitationally bound, orbiting each other. Observing asteroid moons requires careful astronomical work. Most asteroids are too small and distant to be resolved as disks even through powerful telescopes. They appear as points of light. Their moons are even fainter and closer to the primary, making direct imaging challenging. However, several techniques reveal their presence. Light curve analysis measures how an asteroid's brightness changes over time as it rotates. A simple asteroid produces a regular, repeating pattern, but if a moon is present, it creates additional dips or bumps in the light curve as it passes in front of or behind the primary asteroid, or as it reflects additional light toward Earth. Radar observations provide another powerful technique. When radio waves are bounced off an asteroid, the reflected signal contains information about the asteroid's shape, rotation, and surface features. If a moon is present, it appears as a separate echo in the radar data, delayed relative to the primary's echo by the light travel time to the more distant moon. The Arecibo Observatory in Puerto Rico and the Goldstone Solar System Radar in California have discovered dozens of asteroid moons through radar observations of near-Earth asteroids as they pass relatively close to Earth. Spacecraft missions provide the most detailed views of asteroid moons. After Galileo's discovery of Dactyl orbiting Ida, subsequent missions have encountered other asteroid systems. The Near-Shoemaker spacecraft orbited asteroid Eros, which has no moon, but provided detailed information about asteroid composition and structure that helped interpret observations of binary systems. The Dawn mission visited the large asteroids Vesta and Ceres, also moonless, but revealed the complex geology of these protoplanets. Future missions specifically targeting binary asteroids will provide unprecedented insights into these systems. The existence of asteroid moons has practical implications beyond pure science. Some near-Earth asteroids pose potential collision hazards to Earth, and understanding whether they have moons affects how we might deflect them if necessary. A binary asteroid system behaves differently than a single asteroid when subjected to external forces. The NASA DART mission, launched in 2021, deliberately crashed a spacecraft into Dimorphos, the moon of the asteroid Didymos, to test whether kinetic impacts could alter an asteroid's orbit, a potential planetary defense technique. The mission successfully changed Dimorphos's orbital period, demonstrating that asteroid moons respond to impacts in measurable ways. The orbital dynamics of asteroid moon systems are surprisingly rich because the gravitational fields are so weak. Other forces become relatively more important. Solar radiation pressure, the physical push exerted by sunlight, can perturb asteroid moon orbits significantly over time. The orbits slowly evolve, sometimes becoming more circular, sometimes more elliptical, depending on the specific configuration. Tidal forces between the asteroid and its moon, though tiny, gradually exchange angular momentum, causing the moon to migrate inward or outward over millions of years, potentially leading to eventual escape or collision. Triple asteroid systems exist as well, where one asteroid has two moons, or where three similarly sized bodies orbit their common center of mass. The asteroid Sylvia, about 260 kilometers in diameter, has two known moons named Romulus and Remus, discovered in 2001 and 2004 respectively. Romulus orbits at about 1,360 kilometers from Sylvia, with an orbital period of 3.6 days. Remus orbits closer, at about 710 kilometers, with a period of 1.4 days. These multiple moon systems provide natural laboratories for studying gravitational dynamics in the weak field limit. The study of asteroid moons illuminates the processes that operated during planet formation. Planets grew through collisions and mergers of smaller bodies, asteroids, and planetesimals. Understanding how these small bodies interact, collide, capture each other, and form bound systems helps us understand the early stages of planet formation. Every asteroid moon is a relic of these ancient processes, a small-scale version of the interactions that built planets from swarms of orbiting debris billions of years ago. The discovery that asteroids can have moons transformed them from simple rocks floating in space into complex, evolving systems with their own orbital dynamics, formation histories, and future fates. These tiny moons orbiting tiny worlds demonstrate that the fundamental laws of gravity and motion operate at all scales, creating structure and dynamics from the largest galaxy clusters down to kilometer-sized rocks tumbling through the asteroid belt. Each small moon a reminder that even the weakest gravity can bind objects together across the emptiness of space. How aliens could breathe different atmospheres. When we imagine aliens visiting Earth in science fiction, they often step out of their spacecraft and breathe our air without difficulty, or they wear helmets and breathing apparatus because our atmosphere is toxic to them. Both scenarios recognize a fundamental truth. The atmosphere that sustains one form of life might be useless or deadly to another. On Earth, oxygen is essential for most complex life, powering the high-energy metabolisms of animals through cellular respiration. But oxygen wasn't always abundant in Earth's atmosphere, and even today, many organisms live without it, thriving in environments where oxygen is scarce or absent. Understanding how aliens could breathe different atmospheres means understanding the relationship between atmospheric gases and metabolism, the chemistry of energy extraction, and the remarkable adaptability that evolution can produce when organisms face different atmospheric conditions. Earth's atmosphere is about 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, water vapor, and other gases. This composition seems normal because it's all we've known, but it's actually quite unusual from a cosmic perspective. Oxygen is highly reactive. It combines readily with many elements, forming oxides that are stable and chemically inert. Free oxygen shouldn't persist in a planet's atmosphere for long unless something continually replenishes it. On Earth, that something is photosynthetic life. Plants, algae, and photosynthetic bacteria capture sunlight and use its energy to split water molecules, releasing oxygen as a byproduct. Without life constantly producing oxygen, Earth's atmosphere would gradually lose its oxygen as the gas reacted with rocks, metals, and organic molecules, eventually leaving an atmosphere dominated by nitrogen and carbon dioxide. For the first 2 billion years, or more of Earth's history, the atmosphere contained very little free oxygen. Early life evolved in this oxygen-poor world, using different metabolic pathways that didn't require oxygen. Even today, many organisms live in oxygen-free environments, deep in ocean sediments, in the intestines of animals, in waterlogged soils where oxygen cannot penetrate. These anaerobic organisms use alternative molecules as the final electron acceptors in their metabolism. Some use sulfur compounds, reducing sulfate to hydrogen sulfide, the gas that smells like rotten eggs. Others use nitrates, producing nitrogen gas. Still others use carbon dioxide itself, producing methane. These metabolisms are less efficient than oxygen-based metabolism, releasing less energy per molecule of food consumed, but they work well enough to sustain life. An alien planet that never developed photosynthetic life might retain an oxygen-poor atmosphere indefinitely. Life on such a world would necessarily use anaerobic metabolism, breathing gases we would consider unusual or toxic. Hydrogen sulfide, lethal to most Earth animals, could serve as the oxidizing agent in alien metabolism. Organisms might inhale hydrogen sulfide and exhale elemental sulfur or some other sulfur compound. Their biochemistry would be built around sulfur chemistry, the way ours is built around oxygen chemistry. These aliens would find Earth's oxygen-rich atmosphere as toxic as we find hydrogen sulfide. Oxygen would react with their sulfur-based biochemistry, disrupting the carefully balanced chemical reactions that keep them alive. Methane represents another possibility. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, and it exists as a gas at temperatures where water is liquid. Some Earth organisms produce methane as a waste product of their metabolism, and these methane-producing microbes, called methanogens, thrive in oxygen-free environments, like swamps, rice paddies, and the digestive systems of cattle. Methane is flammable in the presence of oxygen, but in an oxygen-free atmosphere, it's stable. A planet with abundant methane in its atmosphere might support life that uses methane in its metabolism, perhaps breaking down methane to extract energy or using methane as a raw material to build more complex organic molecules. Titan, Saturn's largest moon, has an atmosphere dense with nitrogen and methane, with no free oxygen. The surface temperature hovers around -180 degrees Celsius, cold enough that water is frozen as hard as rock, while methane exists as liquid in lakes and seas. If life exists on Titan, a big if, but not impossible, it would necessarily be adapted to breathe this nitrogen-methane atmosphere, and might even metabolize in ways that involve liquid methane rather than liquid water. Such organisms would be completely incompatible with Earth's environment. Bringing them to Earth would be like throwing a fish into a furnace. The heat alone would destroy them before oxygen toxicity became an issue. Carbon dioxide-rich atmospheres present another scenario. Venus has an atmosphere that's about 96% carbon dioxide, creating a crushing surface pressure about 90 times Earth's atmospheric pressure and a runaway greenhouse effect that raises surface temperatures to over 450 degrees Celsius. No life could exist in Venus's current conditions, but a cooler planet with a carbon dioxide atmosphere and might be habitable. Some Earth organisms already tolerate high carbon dioxide levels that would kill humans. Deep-sea hydrothermal vent communities, for instance, experience high carbon dioxide concentrations dissolved in water. Organisms adapted to such environments have specialized biochemistry that allows them to function despite the high carbon dioxide. Aliens from a carbon dioxide-rich world might metabolize in ways that involve carbon dioxide directly. Perhaps they would use carbon dioxide as an oxidizing agent, combining it with hydrogen-rich compounds to extract energy, producing methane or other hydrocarbons as waste products. Or they might use carbon dioxide as a raw material, building organic molecules from carbon dioxide the way plants do, but doing so as part of their metabolic processes rather than as a separate photosynthetic function. These aliens might find oxygen toxic and carbon dioxide essential, the opposite of most Earth animals. Ammonia is another gas that could potentially play a role in alien respiration. Ammonia is toxic to most Earth life, disrupting pH balance and interfering with normal biochemistry. But at lower temperatures, ammonia can exist as a liquid, and some scientists have speculated that ammonia could serve as a solvent for biochemistry on very cold worlds, potentially replacing water. An atmosphere with significant ammonia might support organisms that breathe ammonia, using it in their metabolism in ways we can barely imagine. The chemistry would be entirely different from oxygen-based metabolism, operating through different pathways and producing different waste products. Chlorine and fluorine, both highly reactive halogens, represent more exotic possibilities. These gases are extremely reactive and toxic to Earth life, but that's precisely because they're good at accepting electrons, the same property that makes oxygen useful for metabolism. An organism that evolved in an atmosphere containing chlorine or fluorine might use these gases the way we use oxygen, combining them with food molecules to extract energy. The waste products would be chlorides or fluorides rather than the water and carbon dioxide that Earth animals produce. Such organisms would find Earth's atmosphere lacking. Our oxygen, while reactive, wouldn't fit into their chlorine-based or fluorine-based biochemistry. They would suffocate in our air despite it containing a highly reactive gas. The partial pressure of gases matters as much as their chemical identity. Partial pressure is the pressure contributed by a specific gas in a mixture. For instance, Earth's atmosphere has a total pressure at sea level of about 1 atmosphere, and oxygen makes up 21% of that. So oxygen's partial pressure is about 0.21 atmospheres. Humans need oxygen at roughly this partial pressure to survive. Too little at high altitudes where atmospheric pressure drops and we suffer hypoxia, unable to get enough oxygen into our blood. Too much in pure oxygen at high pressure, and oxygen becomes toxic, causing seizures and lung damage. Aliens would have similar constraints based on their biochemistry. An alien that breathes hydrogen sulfide might need it at a specific partial pressure. Too little, and their metabolism cannot function efficiently. Too much, and it becomes toxic even to them. This means that even if two species breathe the same gas, they might not be able to share the same atmosphere if they require different partial pressures. An alien adapted to breathe oxygen at very low partial pressures, perhaps from a high-altitude environment or a planet with thin atmosphere, might suffocate in Earth's oxygen-rich air, not from lack of oxygen, but from oxygen toxicity. Temperature affects which molecules can exist as gases. On Earth, at our range of temperatures, nitrogen, oxygen, carbon dioxide, and water vapor exist as gases while water also exists as liquid. On a much hotter planet, perhaps one close to its star, gases we don't encounter might be common. Sulfur compounds that are liquids or solids on Earth might be gases on a hot world. Metals like mercury or even iron could exist as vapor in the atmosphere of an extremely hot planet. Life on such a world, if it could exist at all, might breathe exotic gases that would condense into liquids or solids in Earth's relatively cool atmosphere. Conversely, on extremely cold worlds, gases that are common on Earth might be frozen solid. On Pluto, where temperatures drop to around -230 degrees Celsius, nitrogen, which makes up most of Earth's atmosphere, freezes into solid nitrogen ice. Pluto's thin atmosphere consists of nitrogen, methane, and carbon monoxide that sublimates from surface ices when Pluto is closest to the Sun in its elliptical orbit, then freeze back out when Pluto moves farther away. Life on such a cold world would need to breathe gases that remain gaseous at these extreme temperatures, or it would need to exist in warmer subsurface environments where different conditions prevail. The evolution of breathing mechanisms would differ based on atmospheric composition and pressure. On Earth, animals evolved lungs, gills, tracheal systems, and other specialized structures to extract oxygen from air or water. Fish gills expose blood to water flowing past thin membranes, allowing oxygen to diffuse from water into blood. Insect tracheal systems deliver air directly to cells through branching tubes. Mammalian lungs use millions of tiny air sacs to maximize surface area for gas exchange. Each system is optimized for extracting oxygen from Earth's atmosphere or water. Aliens breathing different atmospheres would evolve different respiratory structures optimized for their specific gases. An alien breathing a very dense atmosphere, perhaps with pressures many times Earth's, might have very small respiratory surfaces because gases would diffuse quickly at high pressure. An alien breathing a thin atmosphere might need enormous respiratory organs to capture enough of their necessary gas. An alien breathing a gas that dissolves poorly in their body, fluids might need respiratory pigments, molecules like hemoglobin in our blood, specifically designed to bind and transport their particular gas. Some aliens might not breathe at all in the sense of moving gases in and out of their bodies. Single-celled organisms on Earth absorb oxygen directly through their cell membranes without any respiratory system. An alien with a radically different body plan, perhaps resembling Earth's sponges or fungi more than animals, might absorb needed gases through its entire surface area, rather than through specialized breathing organs. Or an alien might rely entirely on anaerobic metabolism happening within its cells, never needing to extract gases from the environment at all, living on chemical energy stored in molecules absorbed from its surroundings. The possibility of breathing different atmospheres means that habitable zones around stars become more complex. The traditional habitable zone focuses on temperature, the range where liquid water can exist. But a habitability zone could be defined for any solvent and any metabolic gas. There's a methane habitability zone at different temperatures where methane is liquid. There's a hydrogen sulfide habitability zone where that gas exists at suitable pressures. There's an ammonia habitability zone at very cold temperatures. Each zone would support fundamentally different kinds of life adapted to its specific conditions. If humans ever encounter aliens, the atmospheric incompatibility would be one of the first obvious differences. We couldn't share environments without life support equipment. An alien from an ammonia world would need refrigeration and ammonia supplies to survive in Earth's environment. We would need oxygen supplies and temperature regulation to survive in theirs. Even communication would be affected. Sound travels differently in different atmospheric gases. In a dense carbon dioxide atmosphere, sound would be lower pitched and quieter. In a thin hydrogen atmosphere, sound would be higher pitched and travel faster. An alien's voice might be physically impossible for human ears to hear without electronic translation. How aliens could breathe different atmospheres ultimately reflects the diversity of chemistry and the flexibility of evolution. Life adapts to available conditions, and the chemistry that powers metabolism is not limited to oxygen and carbon dioxide. From hydrogen sulfide to methane, from ammonia to chlorine, from thin atmospheres to crushing pressures, from scorching heat to numbing cold, life, if it exists elsewhere, would develop respiratory systems suited to its world's specific conditions, breathing atmospheres that might kill us in seconds, while finding our oxygen-rich air as toxic and alien as we would find theirs, proving that the breath of life can take as many forms as there are worlds scattered across the universe. How black holes warp time itself. Time is not the constant, uniform flow that our everyday experience suggests. It can stretch, compress, and slow down, depending on the gravitational environment you're in. Nowhere is this more extreme than near a black hole, where gravity becomes so intense that time itself warps, in ways that challenge our intuition and transform our understanding of reality. Understanding how black holes affect time means grappling with one of the most profound insights of modern physics, that space and time are not separate, fixed stages on which events unfold, but rather a unified fabric that can be bent, twisted, and stretched by the presence of mass and energy. The foundation for understanding time dilation near black holes comes from Albert Einstein's general theory of relativity, published in 1915. Einstein proposed that what we perceive as gravity is actually the curvature of space-time caused by mass and energy. Massive objects create depressions in the fabric of space-time, much like a bowling ball placed on a stretched rubber sheet creates a depression that affects how nearby marbles roll. This curvature affects not just the paths that objects follow through space, but also the rate at which time passes. The basic principle is that time passes more slowly in stronger gravitational fields. This effect, called gravitational time dilation, has been confirmed through countless experiments. Atomic clocks placed at different altitudes on Earth tick at measurably different rates. Clocks at sea level run slightly slower than clocks on mountaintops, because they're deeper in Earth's gravitational well. The difference is tiny, only nanoseconds per day, but it's real and measurable. GPS satellites must account for this effect. Without corrections for gravitational time dilation, GPS coordinates would drift by several kilometers per day. Near a black hole, gravitational time dilation becomes extreme. Imagine two observers, one hovering far from a black hole in weak gravity, the other hovering closer to the black hole, where gravity is much stronger. If both observers synchronize their watches and then separate, the watch closer to the black hole will tick more slowly from the distant observer's perspective. This isn't an illusion or a malfunction of the watch. Time genuinely passes more slowly in the stronger gravitational field. The closer you get to a black hole, the more severe this effect becomes. At the event horizon, the boundary beyond which nothing can escape, time dilation becomes infinite from the perspective of a distant observer. This creates one of the most counterintuitive aspects of black holes. If you were to watch someone fall toward a black hole while you remained safely far away, you would see something strange. As the falling person approached the event horizon, they would appear to slow down. Their movements would become sluggish, their signals would take longer to reach you, and their image would become increasingly red-shifted as the light they emit is stretched by the intense gravity. From your distant vantage point, the falling person would never quite seem to cross the event horizon. They would appear to freeze at the boundary, becoming dimmer and redder until they faded from view entirely. This isn't because they stopped falling. From their own perspective, they would cross the event horizon and continue falling inward in a finite amount of time, experiencing nothing unusual at that precise moment. The difference is entirely due to how time flows differently in different gravitational fields. This discrepancy between what the falling observer experiences and what the distant observer sees is one of the most mind-bending aspects of general relativity. Both perspectives are equally valid. The falling observer crosses the event horizon in, say, 10 seconds by their clock, but from the distant observer's perspective, watching that crossing would take infinite time. It would never be complete. This isn't a contradiction, but rather a demonstration that time is not absolute. Different observers in different gravitational fields experience time at different rates. The mathematics describing this time dilation near black holes was first worked out by Carl Schwarzschild in 1916, just months after Einstein published general relativity. Schwarzschild found an exact solution to Einstein's equations describing the spacetime around a non-rotating, spherically symmetric mass, what we now call a Schwarzschild black hole. His solution showed that time dilation increases as you approach the event horizon, located at what's now called the Schwarzschild radius, reaching infinite dilation exactly at the horizon. For a rotating black hole, described by the Kerr solution, found by Roy Kerr in 1963, the situation becomes even more complex. Rotation creates additional effects beyond simple time dilation. The black hole drags spacetime around with it in a process called frame dragging. Close to a rotating black hole, space itself is pulled around in the direction of rotation. You couldn't remain stationary, even if you wanted to. You'd be forced to rotate with the spacetime itself. This creates regions like the ergosphere outside the event horizon, where frame dragging is so strong that everything must move in the direction of the black hole's rotation. The warping of time near black holes has practical implications for anything orbiting or falling toward them. Consider material in an accretion disk spiraling into a black hole. Material in the inner portions of the disk, closer to the black hole, experiences stronger time dilation than material farther out. From the perspective of an observer far from the black hole, processes in the inner disk appear to run in slow motion compared to processes in the outer disk. This affects how we observe black holes and interpret the light we receive from matter near them. Time dilation also affects the gravitational redshift of light, escaping from near a black hole. Light climbing out of a gravitational well loses energy, its wavelength stretching toward the red end of the spectrum. This gravitational redshift is intimately connected to time dilation. They're two aspects of the same phenomenon. A photon emitted from close to the event horizon will be dramatically redshifted by the time it reaches a distant observer. If the photon is emitted from the event horizon itself, it would be redshifted infinitely, its energy dropping to zero, another way of understanding why nothing can escape from beyond the horizon. Inside the event horizon, the warping of spacetime becomes even more extreme. In this region, the roles of space and time actually exchange in a sense. Outside the horizon, moving forward in time is inevitable. You cannot choose to move backward in time, but you can choose your direction in space. Inside the horizon, moving toward the singularity at the center becomes as inevitable as moving forward in time outside the horizon. All possible paths lead inward, and reaching the singularity becomes as unavoidable as reaching the next moment in time. The singularity at the center of a black hole represents a place where space-time curvature becomes infinite, and general relativity's equations break down. At the singularity, time itself becomes undefined in the classical sense. This suggests that general relativity is incomplete, that a theory of quantum gravity would be needed to properly describe what happens at and beyond the singularity. String theory, loop quantum gravity, and other approaches to quantum gravity propose different solutions to what occurs at this extreme limit, but none have been confirmed experimentally. Supermassive black holes at the centers of galaxies create fascinating time dilation effects on galactic scales. The black hole at the center of our Milky Way galaxy, called Sagittarius A star, contains about 4 million solar masses. Stars orbiting close to this black hole experience measurable time dilation. A star in a close orbit around Sagittarius A star, coming within a few hundred times the black hole's event horizon radius, would experience time flowing noticeably slower than we experience it here on Earth, 26,000 light-years away. Precise measurements of these stars' orbits by Andrea Ghez and Reinhard Genzel, who shared the 2020 Nobel Prize in Physics for this work, have confirmed general relativity's predictions in this strong gravity regime. Time dilation near black holes has captured popular imagination, featuring prominently in science fiction. The film Interstellar depicted a planet orbiting close to a massive rotating black hole, where time dilation was so extreme that 1 hour on the planet's surface equaled 7 years of time passing elsewhere. While Hollywood took some liberties, the basic physics was sound. Physicist Kip Thorne served as scientific consultant and later published papers about the black hole physics portrayed in the film. Such extreme time dilation is theoretically possible near a rapidly rotating supermassive black hole. Binary black hole systems, where two black holes orbit each other before merging, create incredibly complex space-time geometries. Each black hole warps time in its vicinity, and the combined warping creates regions where time flows at different rates depending on your location relative to the two black holes. As the black holes spiral together and merge, events that produce the gravitational waves detected by LIGO and other observatories, the warping of spacetime becomes dynamical, with gravitational waves carrying information about how spacetime is oscillating and rippling during this violent event. The connection between time dilation and energy offers another perspective on these phenomena. According to general relativity, gravitational fields contain energy. A clock deep in a gravitational well, where time runs slowly, can be thought of as having less energy than a clock far from any gravitational source. The gravitational redshift of light, the loss of energy as light climbs out of a gravitational well, reflects this energy difference between different regions of curved spacetime. Black holes also raise profound questions about the nature of time itself. Some interpretations of quantum mechanics and general relativity suggest that time might not be fundamental, but rather an emergent property of more basic physical processes. Black holes, where classical notions of time break down at the singularity, might provide clues about the true nature of time. The information paradox, the question of what happens to information that falls into a black hole, connects to deep questions about time, entropy, and the quantum nature of spacetime. Hawking radiation, predicted by Stephen Hawking in 1974, introduces another connection between black holes and time. Quantum effects near the event horizon cause black holes to emit radiation and slowly evaporate over extremely long timescales. This process involves virtual particle pairs appearing near the horizon, with one particle falling in while the other escapes. The evaporation means black holes have a finite lifetime, and it connects quantum mechanics, gravity, and thermodynamics in ways that hint at a deeper theory unifying these domains. The warping of time near black holes is not science fiction, but established physics, confirmed through observations and experiments. Every time LIGO detects gravitational waves from merging black holes, it's detecting ripples in spacetime that carry information about how dramatically spacetime, and therefore time itself, was warped during the merger. Every observation of matter orbiting near black holes, every measurement of gravitational redshift, every test of general relativity in strong gravitational fields, confirms that time is not absolute, but is woven into the fabric of spacetime, susceptible to warping and stretching by mass and energy, reaching its most extreme manifestation near black holes, where the flow of time slows to a crawl, and ultimately, at the event horizon, appears to stop entirely from the perspective of distant observers watching the inexorable pull of gravity on the fabric of reality itself. How fast you'd need to go to leave a planet. Every object massive enough to have significant gravity holds onto anything near its surface. A ball thrown upward eventually falls back down. A bird must constantly flap its wings to stay aloft. Even the fastest jet aircraft cannot fly into space. Eventually it runs out of altitude and must descend. To truly leave a planet, to escape its gravitational grip entirely and coast into space without using any more fuel, you must reach a specific speed called escape velocity. This critical speed depends on the planet's mass and size, and understanding it reveals why launching rockets is so difficult, why some worlds can hold atmospheres while others cannot, and why the smallest push can send an astronaut drifting away from an asteroid while escaping Earth requires enormous rockets burning millions of pounds of fuel. Escape velocity is not about reaching a particular altitude or getting above the atmosphere. It's about speed, specifically moving fast enough that your kinetic energy equals or exceeds the gravitational potential energy binding you to the planet. If you launch something straight up at exactly escape velocity, it will climb higher and higher, slowing down continuously as gravity pulls it back, but never quite stopping. It will coast to infinite distance, arriving there with zero velocity, having converted all its initial kinetic energy into potential energy. Launch at any speed less than escape velocity, and gravity eventually wins, pulling the object back down. For Earth, escape velocity at the surface is about 11 kilometers per second, roughly 40,000 kilometers per hour, or about 25,000 miles per hour. This is more than 30 times faster than a typical passenger jet flies. To reach this speed, starting from rest requires enormous amounts of energy, which is why rockets are so large and burn so much fuel. The Saturn V rocket that launched Apollo missions to the Moon stood over 100 meters tall and weighed more than 2,000 tons at launch. But only about 50 tons of that mass, less than 3%, was the actual Apollo spacecraft and crew. Everything else was fuel and engines needed to accelerate that relatively small payload to the speeds necessary for spaceflight. Escape velocity depends on two factors: the planet's mass and its radius. More massive planets have higher escape velocities because stronger gravity pulls harder, requiring more speed to escape. Larger planets, meaning planets with larger radii, have lower escape velocities at their surfaces because you start farther from the center of mass where gravity is weaker. Earth is more massive than Mars, but also larger, and the combination means Earth's escape velocity is about 4.5 kilometers per second, higher than Mars's escape velocity of roughly 5 kilometers per second. This makes Mars somewhat easier to launch from than Earth. A rocket leaving Mars needs to reach only about half the speed required to leave Earth, which translates to roughly 1/4 the energy. Energy requirements scaled with the square of velocity. Mars's thinner atmosphere also helps, creating less air resistance during ascent. These factors make Mars an attractive location for future space missions that might launch from the surface to explore the outer solar system or return to Earth. The Moon, much smaller and less massive than Earth, has an escape velocity of only about 2.5 kilometers per second, less than 1/4 Earth's escape velocity. This made the Apollo lunar module's ascent from the Moon's surface relatively straightforward compared to launching from Earth. The ascent stage needed far less fuel and could use a much smaller engine. The low escape velocity also meant that the lunar module could take off without the massive multi-stage rockets required for Earth launch, using a single engine to reach lunar orbit directly. Jupiter, the most massive planet in our solar system, has an escape velocity from its cloud tops of about 60 kilometers per second, more than 5 times Earth's escape velocity. Launching from Jupiter, if there were a solid surface to launch from, would require vastly more energy than launching from Earth. Any spacecraft falling into Jupiter's atmosphere would need extraordinary speeds to escape again, which is why missions to Jupiter use gravity assists from other planets to gain speed rather than attempting to enter and exit Jupiter's deep gravity well. The concept of escape velocity explains why planets can hold atmospheres, while asteroids and comets cannot. Gas molecules in an atmosphere move at speeds related to temperature. Hotter gases move faster. For an atmosphere to remain bound to a body over billions of years, the typical speed of atmospheric molecules must be significantly lower than escape velocity. If molecules regularly reach speeds close to or exceeding escape velocity through random thermal motion, they leak away into space. Earth's atmosphere consists primarily of nitrogen and oxygen molecules that move at average speeds of a few hundred meters per second at normal temperatures, well below escape velocity. The lightest element, hydrogen, moves much faster at the same temperature because lighter molecules move faster for a given thermal energy. Hydrogen molecules at Earth's atmospheric temperature move at average speeds around 2 kilometers per second, which is still well below escape velocity, but close enough that over billions of years, Earth has lost most of its primordial hydrogen. The Moon's escape velocity is low enough that essentially no gas can remain in a lunar atmosphere. Any molecules would need to be extremely cold to have velocities below escape velocity, but solar heating warms the lunar surface during the long lunar day, giving molecules enough energy to escape. This is why the Moon has no atmosphere. Its weak gravity cannot hold even the lightest gases against thermal evaporation. Mars, with escape velocity between the Moon's and Earth's, represents an intermediate case. Mars can hold heavier molecules, like carbon dioxide in its atmosphere, but it loses lighter molecules more easily. Mars also lacks a strong magnetic field to protect its atmosphere from the solar wind, the stream of charged particles from the Sun. Over billions of years, the solar wind has stripped away most of Mars's original atmosphere, leaving the thin atmosphere we observe today. Escape velocity decreases with altitude. At the surface, you need to reach Earth's full escape velocity of 11 kilometers per second. But at the altitude where the International Space Station orbits, about 400 kilometers up, escape velocity is slightly less, around 10.9 kilometers per second. The difference is small because 400 kilometers is not much compared to Earth's radius of about 6,400 kilometers. But at lunar distance, about 380,000 kilometers, escape velocity from Earth has dropped to only about 1 kilometer per second. Apollo spacecraft needed to reach only this lower speed to escape Earth's gravity after coasting most of the way to the Moon. Escape velocity is the same in all directions. You could launch straight, up, horizontally, or at any angle, and you'd need the same speed to escape. The direction doesn't matter for escape, only the speed. However, in practice, rockets don't launch straight up. They curve their trajectory to gain horizontal velocity as well as altitude, because horizontal velocity is what's needed for orbit. Reaching escape velocity while moving horizontally means you escape while also having momentum that carries you away from the planet, rather than climbing straight up until you barely escape with zero velocity. Black holes represent the extreme case of escape velocity. At the event horizon, the boundary of a black hole, escape velocity equals the speed of light. Nothing can move faster than light, so nothing can escape from within the event horizon. This is what makes a black hole black. Not even light can escape once it crosses this boundary. For a black hole with a few times the Sun's mass, the event horizon has a radius of only about 10 kilometers. The extreme compression of mass into such a small radius creates escape velocities that reach and exceed the cosmic speed limit. Interestingly, you don't have to reach escape velocity to get into space. Rockets reaching orbit around Earth need to achieve only about 8 kilometers per second at orbital altitude, less than escape velocity. Orbital velocity is the speed at which your sideways motion exactly balances gravitational pull, so you continuously fall around the planet rather than falling back to it. This is easier to achieve than escape velocity, which is why orbital missions are more common than interplanetary missions. The Space Shuttle, for example, accelerated to about 8 kilometers per second, to reach low Earth orbits, then used additional fuel to accelerate to higher speeds only when needed for missions to higher orbits or to the International Space Station. Missions leaving Earth orbit for the Moon, Mars, or other destinations required additional speed beyond orbital velocity to reach escape velocity and break free of Earth's gravity. Understanding escape velocity also explains how gravity assists work. When a spacecraft flies past a planet on a carefully calculated trajectory, it can gain speed by essentially stealing a tiny amount of the planet's orbital momentum. From the spacecraft's perspective, it falls toward the planet, swings around it, and flies away. If the trajectory is chosen correctly, the spacecraft leaves moving faster relative to the Sun than it arrived, having been accelerated by the planet's gravity without burning any fuel. The Voyager spacecraft used multiple gravity assists from Jupiter and Saturn to reach speeds high enough to eventually escape the solar system entirely, crossing into interstellar space decades after launch. Calculating how fast you'd need to go to leave a planet comes down to a simple formula involving the planet's mass and radius, derived from Newton's law of universal gravitation. The energy required to escape grows with planetary mass and shrinks with planetary radius, creating the variety of escape velocities we observe throughout the solar system. From tiny asteroids where you could literally jump into space if you weren't careful, to massive Jupiter where even the most powerful rockets would struggle to escape, the speed required to leave a world tells us about that world's fundamental properties and shapes everything from how we design spacecraft to which worlds can hold atmospheres, determining the accessibility of each destination in our cosmic neighborhood and beyond.